You know, when you think about how fast a wave is moving, you probably think of one single, simple rule. Well, today we're going to dig into how waves really move. And it turns out sometimes the most important speed is the one you can't actually see.
It sounds like the start of a weird joke, doesn't it? But trust me on this. The answer reveals something fundamental and, frankly, kind of weird about physics. Stick around and you'll see exactly what I mean.
Okay, so first things first, let's start with the stuff most of us remember from high school physics class. It's a beautifully simple rule that, for the most part, tells us how waves work. So, to build this rule, you really just need three key pieces. The first one is wave speed, which we call v. It's pretty straightforward. It's just how fast a wave is moving through something, like air or water. Next up, we've got frequency, or f. Picture yourself standing on a beach and counting how many waves wash over your feet every second. That's basically frequency. We measure it in hertz. And the last piece of our puzzle is wavelength, which we write down with the Greek letter lambda. This is just the physical distance from the peak of one wave to the peak of the very next one. So you put those three things together, and boom, you get this super elegant equation. Speed equals frequency times wavelength. It's clean, it's simple, and it's a bedrock concept in physics. And here's the key takeaway from this, right? It's this inverse relationship. If the speed of the wave is constant, like the speed of light, which never changes, and you crank up the frequency, the wavelength has to get smaller to compensate. It's exactly why gamma rays have these teeny tiny wavelengths compared to giant radio waves, even though they're both zipping along at the exact same speed. Okay, so everything seems nice and neat, right? Well, here's where our perfect little rule starts to get complicated. Because in the real world, you're almost never dealing with just one perfect, simple wave. So what happens then? Yeah, when you get a bunch of waves all moving through the same space, they mash up and interfere with each other. And what you get is something called a wave packet. And this is where our simple rule kind of breaks down. Because a wave packet doesn't just have one speed. So think of a wave packet as having two distinct parts. You've got the high-frequency waves kind of buzzing along on the inside, but all together, their combined shape creates this bigger, overarching form. And that outer shape is what we call the envelope. So this raises a really, really important question. If you want to know how fast this whole thing is moving, which part are you supposed to track? The tiny waves whipping around inside, or the overall packet that's holding them all together? Because they're moving at different speeds. And the answer, which is kind of wild, is you track both. They're both real speeds. Physics just gives them two different names to keep them straight: phase velocity and group velocity. Let's break them down. All right, so let's just lay it out side by side. Phase velocity, that's the speed of those little individual crests inside the packet. Think of it as the tiny ripples. Group velocity, on the other hand, that's the speed of the whole thing, the entire envelope. This is the one that's actually carrying the energy, almost like a package getting delivered. So to put it a little more formally, phase velocity is just the speed of one specific point on the wave, like if you were to pick a single peak and watch it move through space. And group velocity, that's the speed of the packet's overall shape. And this is super important. If that wave is carrying any kind of information or energy, it's the group velocity that tells you how fast that information is actually getting from point A to point B. Okay, I know this can all sound a little bit abstract, so let's bring it down to earth with this absolutely brilliant real-world analogy that's going to make it all click. And a big shout out to Reddit user BigExample5036 for this one. They suggested thinking about what happens when you watch a video of an airplane propeller as it starts to spin up, going faster and faster. Okay, here's how it breaks down. 1, the propeller's real speed, how fast it's actually physically spinning, that's the group velocity. 2, your camera, it isn't recording continuously, right? It's taking snapshots at a fixed frame rate. So it's only catching the propeller's position, or its phase, at specific moments. And so, 3, the speed you think you're seeing in the video, that's the phase velocity. And that right there is why you get that bizarre visual illusion. The motion you see on the screen, the phase velocity, it can look like it's slowing down, or it's standing perfectly still, or even going backwards. And this is all happening while the actual speed of the propeller, the group velocity, is just getting faster and faster. What you see is not what you get. Okay, so what? Why does any of this actually matter? I mean, it's a cool illusion, but is there more to it?
Absolutely. Because this isn't just some party trick with a camera. When you get into the world of quantum mechanics, this difference is everything.
So get this. In quantum mechanics, a particle like an electron is actually described as a wave packet. Its group velocity, that's its real speed through space. And just like everything else with mass, it's got a hard speed limit, the speed of light. It can't go any faster. But the phase velocity, those little waves on the inside, they aren't carrying information. They're not the real particle. And because of that, they're not bound by Einstein's rules. They can and often do appear to travel faster than light.
And that just leaves us with this incredible, mind-bending question to chew on. We've established that the real thing, the particle itself, can't break the speed of light. That's its group velocity. But if its phase can go faster than light, what does that even mean? It really makes you wonder, what's the actual difference between an illusion of motion and motion itself? And that question, well, that's right at the very heart of modern physics.